Hi, I'm David Mueller, retired hydrologist from the U.S. Geological Survey, founder of Genesis Hydrotech, and developer of QRevMS. ADCPs are commonly used for moving boat measurements, and while the moving boat approach is the best approach in many situations, there are some situations where the moving boat approach cannot be used. An alternative to the moving boat approach is to use the mid or mean section methods with an ADCP rather than with a point velocity meter. The advantage of the ADCP for the mid and mean section methods is that it measures a profile rather than discrete point velocities. Situations where the mid or mean section methods are appropriate include rivers with ice cover, when there is difficulty bottom tracking and GPS cannot be used, and when the ADCP cannot accurately measure depth. In addition, when a moving bed approach can be used, but a check measurement is required, the mid or mean section method is appropriate for the check measurement. The data collection for mid and mean section methods is the same. ADCPs are collected at fixed locations, usually 20 to 25 locations, distributed across the cross-section, and the depth, distance from start bank, and the mean velocity for each location is determined. The difference between mid and mean section methods is how the discharge is computed from these fixed measurements. For the mid-section method, the data collected at a fixed location is assumed to be the mean depth and velocity for a panel extending half the distance to the previous fixed location and half the distance to the next fixed location. Thus, to obtain the discharge at a fixed location, the depth and mean velocity measured for the fixed location is multiplied by the average of the previous and next locations. The mean section method computes the discharge for a panel between two fixed locations, beginning at the start bank and working towards the end bank. The discharge is computed by multiplying the average depth and velocity for the fixed location and the next location by the width between the location and the next location. The result is a discharge between two fixed locations, rather than a discharge assigned to a fixed location as in the midsection method. ISO 748 provides a description of both methods. The goals in developing QRevMS were to process data collected using SONTEC and TRDI ADCPs and software, create a user interface that was as close to QRevInt as possible, provide a logical workflow, provide the ability to view and filter ensemble data for each station, compute a mean profile using consistent methods, apply automated extrapolation algorithms to each station, allow the user to specify an ice exponent different from the default value, provide consistent computations for mid and mean section measurements, provide automated data quality assessment and feedback similar to QRevInt, provide manual overrides to all automated filters, and provide an estimate of measurement uncertainty. QRevMS is basically QRevInt for the mid and mean section methods of using the ADCP. QRevMS supports post-processing of data collected by TRDI Section by Section Pro, SONTEC's River Surveyor Stationary Live, and RSQ in stationary mode. The user interface for QRevMS should be very familiar to QRevInt users. The colors, icons, and most tabs are the same as QRevInt, with some modification of content and options to support the mid and mean section methods. Other videos in this series will cover the user interface and emphasize where it differs from QRevInt. The use of QRevMS should be relatively easy for users of QRevInt. QRevMS provides access to view, filter, and evaluate the ensemble data used to compute the mean velocity and depth for each station. Automatic filters are applied independently for each station. QRevMS applies a consistent naming convention to the three velocity methods, which may have different names in the manufacturer's software. The fixed method, called Y velocity by TRDI and XYZ by SONTEC, requires the ADCP to be held in a fixed orientation aligned with the primary direction of flow, x-axis for the SONTEC ADCPs, y-axis for TRDI ADCPs. This method is often used for measurements under ice where the ADCP is inserted into the flow through a hole in the ice. The azimuth method, called 2D velocity by TRDI and ENU by SONTEC, requires the user to provide an azimuth from the left bank to the right bank, perpendicular to the direction of flow. The component of the measured velocity perpendicular to the azimuth is computed and used as the velocity for each station. This is the recommended method if the ADCP has a compass and the site conditions allow accurate ADCP compass headings to be measured. The magnitude method, called the same by TRDI and not available from SONTEC as of September 2024, can be used if the ADCP cannot be held in a fixed orientation and the ADCP has no compass or site conditions prohibit accurate ADCP headings to be measured due to presence of magnetic interference. When using the magnitude method, it is the user's responsibility to measure any angles of flow to the cross-section and enter those angles and/or correction coefficients. Computing the mean profile is simple when the depth cells have a uniform size and depth. The simple mean of the speed, U component, and V component, and for each beam the signal strength, is computed for each depth cell in the profile. The final profile consists of mean values for those cells that have the number of valid ensembles that exceeds the minimum number of valid ensembles set in QRevMS. Although the ADCP should be held in a relatively fixed position, and the depth and velocity should be consistent, small changes in location and turbulence may cause the auto-adaptive modes found in the River Ray, River Pro, Rio Pro, M9, S5, and RS5 to change water modes, which may result in inconsistent cell size at a vertical. Currently, the manufacturers in QRev handle this situation differently. QRevMS determines the cell size that occurs most frequently in the data collected at a station. This cell size becomes the target cell. For TRDI ADCPs with surface cells, the surface cells are recognized and handled as surface cells when positioned above the topmost target cell. The mean velocity components and signal strength values are computed for each cell using a cell size weighted average. If the cell size in an ensemble is larger than the target cell size in the profile, the velocity from the ensemble is used with the cell size of the profile as the weight in the weighted average. If the cell size in an ensemble is equal to or smaller than the target cell size, the cell size of the ensemble is used as the weight for the weighted average. The figure on the right shows the profile cell sizes in the first column and ensemble cell size in the other three columns. This example shows the target profile will have two surface cells followed by larger regular cells. The cell size varies for each of the three ensembles. To compute the mean values for the first cell in the profile, the value in ensemble 1 is multiplied by the size of cell 1 in ensemble 1, since they are the same size. The value in cell 1 of ensemble 2 is multiplied by the size of the profile cell 1 cell size, since the cell size for ensemble 2 is larger. The value in ensemble 3 cell 1 is multiplied by the cell size of ensemble 3 cell 1, since it is the same size as the cell size of the profile cell 1. The sum of these is divided by the sum of the cell sizes used as weights. For profile cell 3, the first ensemble, cell 3, is the same size, so the value in ensemble 1, cell 3, is multiplied by the size of ensemble 1, cell 3. For ensemble 2, we have a similar situation, where the ensemble 2 cell size is greater than the profile cell 3, so the size of the profile cell 3 is multiplied by the velocity of ensemble 2 cell 1. Ensemble 3 presents a different situation. The cell sizes in Ensemble 3 are smaller than the profile cell size for cell 3. For this situation, the values and cell sizes for Ensemble 3, cells 3 and 4, are both used. Although more complex, this approach makes use of all available data and gives equal weight to the data depending on cell size. The result is a profile that is representative of the data collected, even though the cell sizes may vary among the ensembles. QRevMS automatically fits the extrapolation methods to each station using the same algorithms as QRevInt did for the whole measurement. The interface has been adjusted to accommodate this change and the ability to customize the exponent if the water surface is covered by ice. It has been interesting to see how much the profiles vary across the cross-section. In this example, we see that the profile near the left bank deviates from the typical power curve the most, and then towards the center of the channel, the profile approaches the standard power curve with a 1/6 exponent. This is what we would expect. The profiles nearest the channel banks have an influence from the bank shape and roughness, and those near mid-channel for a wide stream approach the more theoretical shape due to the diminished influence of the banks. The deviation from the 1/6 power curve varies by just over 2%. For measurements made through ice, QRevMS distinguishes between solid ice and slush ice in the graphs based on the data provided by the user. QRevMS also provides the user the ability to change the ice exponent from the default 1/6 value. Currently, QRevMS does not automatically compute an ice exponent, but uses the default value of 1/6. The velocity correction factor is another area where the manufacturers and QRevMS differ. The velocity correction factor is a percentage of the normal velocity from the nearest measured station that is used by the velocity for a non-measured station, typically the edge. The velocity correction factor is also commonly used around bridge piers where measurements are difficult. Thus, for a measured station, there should be no use of the velocity correction factor. However, SonTek uses the velocity correction factor for measured stations, and it can be used to increase or decrease the mean velocity for that station. QRevMS does not support this application of the velocity correction factor. In QRevMS, the velocity correction factor can only be used for a manually entered station or at an unmeasured edge, and it defaults to 0. For the mean section method, the computation at the edges of the channel may make use of an edge coefficient. This is another area where the manufacturers differ in their application. As of September 2024, SonTek does not support the use of an edge coefficient when using the mean section method. They compute the edge the same as every other panel. This approach effectively results in a constant edge coefficient of 0.5. Changing the velocity correction factor for the edge has no effect when using the mean section method. TRDI and QRevMS follow the approach used in the moving boat method and assume a default edge coefficient of 0.707. On the Edge tab in QRevMS, the user can set the edge coefficient if using the mean section method. The table on the upper left shows the edge station, the next station, and the panel in between. For the midsection method, the Edge tab allows the user to change the velocity correction factor, which defaults to 0. If the depth at the edge is greater than 0, it is the user's responsibility to provide the appropriate correction factor. The table in the upper left shows the edge station and the measured station adjacent to the edge. The display of midsection mean values and discharges is consistent with the manufacturer's software, where each station and the associated mean values and discharge are displayed on a single line in a table. However, For the mean section method, QRevMS displays the discharge and mean values used to compute the discharge on a separate line from the values measured at the stations. This display method accurately represents the measured data and the location and mean values used to compute the discharge for the panel between the measured stations. For more detailed presentations on QRevMS and the user interface, please view the other videos on using QRevMS, which are linked in the description below. If you have questions or comments, you can leave them in the comments below or contact me through the information on the web page.